All right, welcome back. We are now into Unit 10, where we're going to be talking about climate data. So our goals for this lesson are for you to be able to explain how climate change can be measured and understand the sources of the data that we have about climate. So I think pretty straightforward there. So we can get right into it. So we've been talking in previous lessons about the theory behind climate change. What are the processes that are affecting our global climate? And so you might be thinking, well, this all makes sense in theory, but is this really happening? Do we have direct information, direct measurements of things happening on the Earth that align with our understanding of climate processes? And the answer, of course, is yes. And we have data for different stages in the process of climate change. So we're measuring different things and seeing how they all line up in this process. So we can measure radiative forcings. So if you recall our last lesson, we're looking at that chart at the end of how much impact different factors would have on change in the climate. So we're looking at things like land use change that alters the Earth's albedo and greenhouse gas emissions that enhance the greenhouse effect, right? So these are kind of the causes of climate change. We can measure the scale of these radiative forcings. Then we can measure changes in the Earth's energy balance. So we can measure the Earth's temperature and the incoming and outgoing radiation that the Earth is experiencing. And then we can measure the impacts of climate change. So we can measure some of the effects that climate change has on the world. So things like changes in precipitation, changes in sea level rise, all these things that we would expect to be caused by climate change, we can measure those too. So we're going to kind of go through these different aspects of climate change and look at how we measure each one of these. So let's start with our radiative forcings. So one of the most important radiative forcings that we're looking at is, of course, changes in greenhouse gases such as CO2 in the atmosphere. So we have direct measurements of the composition of the air, where we took some air and captured it and measured what it was made out of, the proportions of different molecules are in that air, going back into the mid 20th century. And so the most famous of these records is called the Keeling curve, named after Charles Keeling, scientist who began taking these observations. And they've been continued to be taken on a daily basis since the 1950s, when Keeling started to compile this record. You'll be looking at a short video that shows you the actual process that they use to continue to make these observations. And it's significant these observations are being made at Mauna Loa Observatory. So that is in Hawaii. The reason for that is that Mauna Loa is in an optimal place to measure the average composition of the Earth's atmosphere. So if I were to take measurements of the composition of the atmosphere outside my house in Pittsburgh, those measurements would be highly affected by local conditions. So there's a lot of industries here in Pittsburgh that emit CO2 as part of their process. And so if some factory had been increasing or decreasing what they are putting out, that would show up in my local measurements of CO2. But by the time air gets all the way out to Hawaii, in the middle of the Pacific Ocean, where there's not a lot of industry locally in Hawaii, that air has gotten really well mixed. So all of the different CO2 emissions that are happening in all different parts of the world have gotten mixed together and averaged out by the time it gets to Mauna Loa. So the air composition at Mauna Loa is going to be very representative of the global air composition, whereas the air composition here in Pittsburgh is not going to be a good representative of the global average. It's going to be much more affected by local things that are happening here, because we've got a lot of emissions related activities like factories, traffic, etc., real close by right here. So they've been measuring CO2 levels, and when you look at the curve there, you look at the data that they have compiled, we can see a few important things. So one thing that we might notice is that there is this sawtooth or jagged kind of pattern to it. And if you look carefully, you'll see that's an annual cycle. We have this up and down of CO2 over the course of each year. And so that's happening across the whole range of the data that we have here. And so that is due to that fast loop in the carbon cycle. So if you remember our discussion of the carbon cycle, we said we have that fast loop of carbon moving from the atmosphere to the biosphere being taken up through photosynthesis, then the plants get eaten by animals, and then when the animals breathe, they breathe CO2 back out into the atmosphere. So when photosynthesis increases, you're going to see CO2 in the atmosphere decrease, and when photosynthesis decreases, you're going to see more CO2 left in the atmosphere. And if you think about our seasonal cycles, right, we're in the fall right now as I'm recording this, and so photosynthesis in our area is decreasing because lots of trees, their leaves are going from green when they had lots of photosynthetic activity to red, brown, yellow as photosynthesis ends, and then dropping those leaves, right? So there's less photosynthesis going on during the winter. And so you would see a corresponding increase in atmospheric CO2 during the winter because less of it's being pulled out through photosynthesis. And then you would expect to see atmospheric CO2 dip a little bit once the spring hits and trees start putting leaves back on, start sucking up more CO2 through photosynthesis. Right? So you would get this seasonal cycle. And because there are a lot more plants growing in the northern hemisphere, because the northern hemisphere has more land, the global atmosphere's carbon dioxide cycle tends to match what's going on in the northern hemisphere. So it's a little bit offset by things in the southern hemisphere going in the opposite direction, but because there's just so much more land, so much more plants to ramp up in the spring and die back during the fall, you get this annual cycle at Mauna Loa that is kind of dominated by what's going on in the northern hemisphere. So that is the jaggedness to that curve, that really regular up and down over the course of each year due to changes in that fast carbon cycle loop. The other thing you'll see from that diagram is that overall the trend line is pretty steadily upward. So from the late 1950s, when we get our first records, the CO2 concentration was around 315 or so parts per million. So part per million, that's 1/1,000,000th of the atmosphere being CO2. So that's where it was when they started making these records at Mauna Loa. And you can see by today, it's gotten up around the 420s parts per million of CO2. So a pretty substantial increase over that time. And so that's due to the unbalancing of the carbon cycle that we talked about, human activity putting more CO2 into the atmosphere. So all of that, we can see that happening when we look at this data that's been collected over the last half century at Mauna Loa. So we have these direct measurements where we directly take some air and analyze it. We can also use satellite data to help us measure some radiative forcings in the realm of greenhouse gases, because we have satellite platforms that are able to measure releases of gases. So for example, releases of methane from oil and natural gas drilling sites. We have satellites that can detect those releases. And if we have those satellites measuring worldwide, we can add up the specific contributions of certain activities to the addition of these gases into the atmosphere, and therefore calculate the amount of radiative forcing that those gases are going to produce. So what about before the 1950s when we have the Keeling curve? Well, we can get access to older air by using ice cores. So when you have a glacier, and especially if we're thinking about the gigantic ice sheets in places like Greenland and Antarctica, each year you're going to get some snow falling on those areas. And then as those layers of snow build up, they get squashed down by the weight of the snow above them until they form ice. And so that ice is going to have a layered quality. It's going to have progressively newer and newer layers of ice building up on top of it. And you can see them almost like tree rings, right? These different layers of ice that get added to these glaciers. And when this ice forms, it's going to trap air bubbles. Because if you imagine snow falling, snow has a lot of air in it, right? There's a lot of air mixed in with the ice crystals in snow. And so when that snow gets compressed down into ice, it's going to trap some of that air. Some of that air is going to remain as little bubbles in the ice. Those bubbles then become basically little air time capsules. It's a little captured piece of air from the past that is being kept in that ice. So we can get access to that by drilling an ice core. So we can drill down into the ice sheet and then extract this cylinder of ice. And that's what you see in the photo there. Photo from the British Antarctic Survey, where they have drilled this ice core and they're taking it out of the metal tube that it comes out in. So then you can take that ice core and you can analyze it. You can slice it up and put it under a microscope. You can extract air from the bubbles that are in it and analyze that to see what the air was like in the past. So that allows you to extend our record of the composition of the air, therefore the radiative forcings from various greenhouse gases, going much farther back into the past. And so these ice sheets in Antarctica and Greenland are about 40 million years old. So that's kind of the maximum time depth you'd be able to get from these, although the ice cores that we've taken generally are something like 800,000 years, is as far back as we've gotten, but we could theoretically go back farther than that, because that's how long the ice has been building up there and trapping these little bubbles of air that we can then access. So atmospheric gases are one important radiative forcing. We also talked about changes in albedo, changes in how much of the sun's light gets reflected off the Earth's surface without ever being absorbed by the Earth. And this is another case where satellites give us our best measurements of this. So we have the Landsat family of satellites that was first launched. The first Landsat satellite was launched in 1972, and we've continued to, as those satellites have gone out of service, we've added new ones, launched new Landsat satellites, and gives us this nice continuous record. You can also use other satellites that were launched by other organizations, but Landsat's kind of the longest running record that we have, going back into the 70s, and it has a 30-meter resolution. So basically, the pixels in the data that we get from Landsat represent 30 meters to a side square of the Earth. So that's pretty good for looking at global level processes. So we can use these Landsat satellite images to determine the Earth's albedo and then determine whether that albedo is changing. So what you see in the image here is the change in albedo of the Earth over the period from March of 2000 to December of 2011. So over that 11-year period, how much did the albedo of the Earth change? So you can see large areas of the Earth having a decreased albedo. So they're reflecting less of the less of the sun's light away, absorbing more of it. And you see that happening especially in areas like the Arctic Ocean. And we're going to talk a little later in this lesson about something called the ice albedo feedback, which is behind that significant change there. Then there are some other areas, especially over some of the oceans, where you see the albedo increasing. And a lot of that is due to increased cloud cover, right? Because clouds are usually very light colored, right? They're white, so they're reflecting a lot of sunlight back into space. So you can use this satellite data to track changes in the Earth's albedo. If we want to go back farther than that, farther than the 70s, we can try to estimate land cover based on things like historical maps, old photos. That gives us, some indication of some of the changes that have occurred to the Earth's surface prior to these satellite records. It's much spottier data with larger uncertainty attached to it, but it can give us some idea of what was happening before we had satellites continuously monitoring the Earth. Okay, so that's some of our ways of measuring our radiative forcings. What about the energy balance of the Earth? The balance between energy coming in, energy going out, and the resulting temperature of the Earth. Well, we have direct measurements of surface temperature that have adequate global coverage to be able to calculate global temperatures going back to about the 1880s. So by the 1880s, we had enough people across enough of the Earth's surface taking frequent temperature measurements with an actual thermometer, right? So a direct measurement of what the temperature is at that spot on that day. We had an adequate network of that in place by about the 1880s. So we have, little over 100 years worth of good surface temperature measurements data taken directly by thermometers. And on the map, you can see what that network of data looks like for the United States. So this is a map of participants in the Cooperative Observer Program, which is a network of over 11,000 weather stations in the United States. So you have all these people that are recording temperatures on usually like an hourly or even minute by minute basis continuously. They feed that data all in to the federal government that is then able to use that to calculate changes in the overall average temperature for different regions or ultimately for the world when we combine this data with similar data being gathered in other countries around the world. So we've got a lot of these weather stations all across the United States. But one thing you might notice from looking at that map is that the coverage is not even. So there are some areas where the coverage is very dense. We've got tons and tons of stations all packed together really closely. So if you look at Pennsylvania, for example, right, you can barely see the different dots on the map because there are so many of them squished together. But on the other hand, if you look at a place like Nevada, you'll see lots of gaps. So we got plenty of dots there, but there's also gaps in between. They're more spread out. So that's because these are weather stations that exist for other reasons. So a lot of these are airports, for example. So if you've got an airport, you need to be collecting weather data all the time to help your pilots land and take off. And so then, since you're collecting this data anyway, you might as well feed it into the Cooperative Observer Program. All right, so these are all places that have their own reasons for gathering this data for their local location, and then they're just contributing it to the national database. So that means areas where you don't have a lot of people, and if you know anything about Nevada, you know it's mostly desert, lots of areas with very few people living there. You don't have very many people, you don't have anybody there collecting weather data. So we get these geographical gaps in the coverage. So you can't just take all of these numbers and just average them all together, because you're going to have more observations per square mile in Pennsylvania than you do in Nevada. And so that's going to overemphasize whatever's happening in Pennsylvania as compared to what's happening in Nevada if you were just to toss all these numbers into one spreadsheet and take the average of them. You also have to think about at the local scale, these locations are not distributed evenly. So for example, they tend to be in urban areas, but the temperature in an urban area is often different from the temperature in the nearby rural areas. So there are various things that make this data not representative in the form that it initially comes into the Cooperative Observer program. They have to correct for these biases. They have to correct for the fact that some areas have more weather stations than others. They have to correct for the fact that weather stations are located more often in urban areas than rural areas, etc. And so when you do that, there are certain assumptions that have to go into that, certain parameters that you have to use to take this uneven set of real world data and turn it into something that is indicative of the overall conditions. And so these slight differences mean that different organizations with somewhat different models can get somewhat different results. So what you're seeing on the graph there is the annual global mean temperature. So it's the estimate of the average temperature over the entire world over the course of the whole year, calculated by different organizations. So these are some of the major organizations that put all of this data from all of these local weather stations together so that we can see what's going on at the global scale. So some of these are things like the Hadley Center in the UK, NOAA, the National Oceanic and Atmospheric Administration, and then NASA. The GIS temp line there is NASA's calculation, which is slightly different than what NOAA is doing. Berkeley Earth is at UC Berkeley. Was actually begun by some people that were a little skeptical of the averaging that was being done by some of these other organizations, and basically redid the whole thing from scratch, starting with the raw observations, the raw numbers, and calculate how you would have to put those together to get an average. And it turned out that what they got ended up being very close to the other organizations that they were initially kind of critical of. So we have a bunch of different organizations that are putting this data together. And you can see that while they get slightly different results on a year-to-year basis, the overall, by and large, trend that they are seeing is the same. So you can see that those lines, even though some of them tend to go up a little higher or down a little lower on a year-to-year basis, they're finding generally the same trajectory, both the same overall upward slope, but also some of the same year-to-year variations. They tend to agree on which years are a little warmer than previous ones, a little colder than previous ones. They just disagree a little bit about how much warmer or how much colder than usual some of these years are. So broadly in agreement about what's going on. They're using slightly different assumptions about how we put together these inconsistent observations of temperature into this statement about what's going on at the global scale. So in addition to these surface temperature readings, we also have satellite data in the case of temperature as well. And again, that goes back only to the 1970s, so we don't have as much time depth, but we have much more comprehensive coverage of the entire globe. When you have a satellite, the satellite doesn't have to worry about being close to someone who can check the thermometer, doesn't have to worry about the difficulties of taking measurements at sea. The satellite is just orbiting above us, taking continuous measurements of the entire Earth. Another interesting thing that the satellites can do is they can measure temperatures at different levels of the atmosphere. So the temperature records that we were talking about before are all measured at the surface because they're people looking at thermometers, basically. So we're getting surface temperatures, but sometimes we want to know what's going on higher up in the atmosphere. And so satellites are able to measure different levels of the atmosphere. And that's what you see in the little graph to the side of the map there, is the satellites looking at different heights within the atmosphere. Okay, so that's great for, since 1970s with satellites, since the 1880s with thermometer measurements. But what if we want to look farther back than that? What if we want to try to understand what was happening with the Earth's energy budget deeper back into time? Well, we were able to estimate past temperatures using what are called proxies. So a proxy is some other record that we do have that correlates with temperature. So something that we would expect to go up and down along with temperature, and then we can use that to infer what the temperature would have been. So these include things like historical records of temperature that are less systematic than we have since the 1880s. So, people were using thermometers or making observations about things like, what day did the pond freeze over and then thaw out each year, which tells us something about, how cold each year was. Now we have these less systematic historical records. We can look at tree rings. So a tree will add a growth ring every year, and the size of that growth ring will depend on the climate conditions. So some conditions will lead to thick growth rings, some will lead to small growth rings, and so we can look at those tree rings to see what the climate conditions were like going back as far as we have preserved trees. We can look at the growth of coral. So when coral grows, it will grow in different ways during different climate conditions, right? Warm and cold ocean conditions will affect the growth of coral, and it also has the kind of annual rings to it like trees do, so we can look at those kind of records, and we can use that information from our ice cores, looking at the thickness of the ice, the composition of the materials that are in there with the ice, the air that was trapped in the ice. We can use all those things to estimate past temperatures. And so since we're estimating them, there is an error range on it. So in the graph there, you see the big kind of gray area around the line. That is our error range, our uncertainty about exactly the number. And you can see that uncertainty gets wider as you go farther back. Right? So you got a fairly narrow amount of uncertainty close to the present, and then more uncertainty the farther back that we go. But the overall trend is pretty clear on this graph. And so this graph is what's colloquially known as the hockey stick graph, because the shape of the line there kind of looks like a hockey stick. You've got the long handle of the hockey stick, and then you get close to the present, and it shoots up like the blade on a hockey stick. And this is actually the original hockey stick graph, so you can see it only goes up to 1998. So the hockey blade would be even taller if I grabbed a current reconstruction like this, but I thought it was interesting to see. This is the original hockey stick graph that really made clear to people that the temperatures that we're seeing right now, the temperatures that we're measuring now, are much warmer than we've seen in the past 1,000 years. So these reconstructions go back to about the year 1000, and you can see that we are way above what was experienced in that range of our past. That was a big deal and really made the reality of climate change apparent to people. And as I've said, it's only gotten warmer since then. So if we had a modern version of the hockey stick graph, you'd see the line, the hockey stick blade going up even farther there. So that's looking at the last 1,000 years. We can actually go back even farther than that. We have other proxies that can take us back to the beginnings of life on Earth. Now, just as we saw with the hockey stick graph, where the uncertainties got bigger the farther back you go, the same is certainly true if we're going back hundreds of millions of years. So in this case, we're only looking at just sort of the overall really broad trends in the Earth's climate. And we are estimating this using ecological and geological information. So ecologically speaking, we look at what kind of living organisms there were in different parts of the world. We know that certain sorts of organisms are going to live better under different kinds of climate conditions, right? We have warm climate organisms, cold climate organisms, and that can, seeing how those organisms arise and die out in the fossil record, tells us something about the overall climate conditions at that point in the past. We can also look at the formation of different sorts of rock formations. So the formation of certain rocks is going to depend on things like temperature and precipitation. You're going to get different kinds of rocks forming in different sorts of ways under different climate conditions. And so by looking at what kind of rocks we have from different points in the Earth's past, we can get an idea of what the climate conditions were like at that point. So these kind of proxy measurements allow us to extend our understanding of the Earth's climate back to the beginnings of life on Earth. And so that's what you're seeing on the graph there. So the beginning of that graph is around the time that complex life starts to arise on Earth. And you can see at that point, the Earth was quite warm. The average global temperature was quite hot. Then you see eventually we came to a period where it got much colder in the vicinity of 350 to 300 million years ago. And if you remember from an earlier lesson, that is around the time that a lot of the fossil fuels were forming. So at the time that these fossil fuels were forming, our Earth cooled off, and trapping all of that carbon underground, where it's no longer in the atmosphere, no longer contributing to the greenhouse effect, was certainly a factor there. So we got sort of a cool period there. Then we got a warm period as Pangea formed, as the different continents came together to create one supercontinent. Earth got quite warm, cooled off for a bit, then got warm again. You can see another peak in the Cretaceous period. So now we're talking about the end of the era of the dinosaurs. So during the whole Mesozoic, when we had dinosaurs, the Earth was generally much warmer than it is today. Then you can see they've got labeled the Paleocene-Eocene thermal maximum. That's the fancy term for a very warm period that came shortly after the extinction of the dinosaurs. So about 65 million years ago, the dinosaurs went extinct. Mammals took over the Earth. We started out with this period of very warm temperatures, but then you can see since then there's been an overall cooling trend across the period since the dinosaurs departed. So during the era of mammals, we've generally had a downward trend in global temperatures until the very, very, very end of our graph there. You can see that it goes down to a pretty cold point and then comes right back up very sharply. So what you're seeing there is the recent ice ages. So we had the Pleistocene ice ages in fairly recent history of the Earth. It was a very cold period by geological standards, but then right now, as we saw with the hockey stick graph, our temperature has been increasing very quickly, and so that's the sort of bounce up at the end there. So what you're seeing here is the planet cycling between what we call hothouse and snowball conditions. So sometimes the Earth gets very warm, sometimes it gets much colder. And the graph is kind of indicating that by dividing when ice caps could actually exist. So we are in one of those snowball phases right now. Despite the recent warming that we've seen, we're still overall colder as compared to the entire geological history of the Earth, because we do still have ice caps at the North and South Pole. For significant periods of the Earth's history, so for, say, most of the Mesozoic, there was no ice at either pole. The Earth overall was too warm to maintain that ice anywhere on the planet, but today we do have that ice there, so we are in one of those snowball phases, at least for the moment. Okay, so when we talk about our measurements of temperature, we often talk in terms of temperature anomalies. So a temperature anomaly is the difference between the observed temperature and the long-term average. So we calculate our long-term average temperature, and then we compare our current observations to that, and we look at the difference between them. So the difference between the average and the current is the anomaly. So a temperature anomaly helps us see where change is occurring. It tells us if we are warmer than we were in the past or colder than we were in the past, regardless of what that temperature itself is, right? An increase of temperature from 0 degrees to 5 degrees is the same temperature anomaly as an increase from 15 to 20, right? It's still an increase of 5, and it's that increase, or in some cases a decrease, is what we're really interested in when we're looking at how temperatures have changed, right? If we're looking at climate change, we want to focus on those increases or decreases, less so than the overall temperature. So the image that you see there is the surface temperature anomaly for the year 2023 as compared to the reference period of 1991 to 2020. So you always have a long-term average that you're comparing to. So compared to the temperatures from 1991 through 2020, you can see some parts of the Earth in 2023 were significantly warmer. So if you look, for example, at Canada, right, you see there in Canada, you have 2 or 3 degrees warmer than average in 2023. Other places you get some cooling. So in Scandinavia, for example, you see it looks like, you know, half a degree to 1 degree colder than average during 2023. So overall, that year, we had generally warmer temperatures worldwide, but there were a few areas that had colder than average temperatures. And so that is all talking about the temperature anomaly. That doesn't mean that it was, you know, hot in Canada and cold in Scandinavia. It means those areas were different from their historical average by different amounts. So let me give you an illustration with some numbers here. And so rather than talking about temperatures, you know, because we can talk about anomalies with any sort of set of data. So let's step away from temperatures and look at exam scores as a kind of data that you can calculate anomalies from. So let's imagine we have a class where there are 4 exams, each worth the same amount in the final grade. And we've got our 2 students here, Alex and Skylar. So I've got their grades on each exam there, and so then you can calculate their average. Right? So Alex was the better student, had an average of 84 across the 4 exams. Skylar only had an average of 62 across those 4 exams. Then for each exam, you can calculate the anomaly for that exam's score relative to that average across all 4 exams. So for example, Alex's exam 1, they scored an 88. That is 4 points higher than their overall average of 84, so their anomaly is a positive 4. So positive 4-point anomaly on exam 1, whereas Skylar got a 62 for exam 1, which is the same as their overall average, so their anomaly is 0. Exam 2, Alex only got a 72, so that's 12 points below their average, so that's a negative 12-point anomaly. And Skylar scored a 53, which is 9 points below their average, so an anomaly of negative 9. So you'll notice here that Alex had a higher score on exam 2. Right? They got a 72, whereas Skylar only got a 53. But Alex has a larger negative anomaly on exam 2 because even though their score was overall higher, it was farther below their average. Right? So it's the distance from that student's average that matters. So even though Skylar did worse on exam 2, they had a less of a negative anomaly because their average score was so much lower. So that's important to keep in mind because we often see that our biggest temperature anomalies are around the poles. So the Arctic Ocean has been one of the areas that has warmed some of the most on our planet. That doesn't mean the Arctic Ocean is now warmer than, say, the equator. It just means that the distance between the current temperatures and the average is greater than it is near the equator. So the poles are still colder than the equator, but they have warmed by more than the equator has. Okay, so let's now look at some of the consequences of climate change that we can measure. So one important consequence of climate change is changes in ice cover. If the Earth is getting warmer, we're going to see less ice, both ice and snow on the land and sea ice, so ice covering ocean areas such as the Arctic Ocean, which you see in the image there. And so what you can see there is that the white area represents the sea ice extent on October 25th, 2025. So I just grabbed the current sea ice when I was making this recording. So the white areas are the areas that are currently covered by ice in the Arctic. And then the orange line shows the average edge of the ice during the period 1981 to 2010. So that's a historical average extent of that ice. And so when you compare those, you can see there's a lot of dark blue ocean inside that historical median right now. So there are some significant areas of the Arctic Ocean that have no ice right now that historically have usually had ice. So this shows us a decrease in Arctic ice, and this holds up. This is just a snapshot of one particular day, but this holds up across a long-term range of data that we're seeing decreased amounts of ice. And so this is measured by both ground-based observations. So we can, measure the amount of snow that we get and the amount of snow that's sitting on the ground just outside. You can go to a glacier and measure the thickness of the glacier and how far the glacier extends down the valley and so forth. And we also have satellite measurements. So the sea ice extent that you see on the map there, that was based on satellite measurements. Satellite is, looking at the Earth and seeing where there is ice. So we can measure these changes in snow and ice cover. And we know that these will have significant ecological effects on species that are affected by cold and ice. So, one of the famous sort of symbols of climate change is polar bears getting stranded by loss of sea ice. So polar bears need to move around on that sea ice as they go hunting for prey and so forth. And so if that sea ice is melting, they can't do that. That is bad for polar bears. On the other hand, reduced amounts of ice and snow are great for ticks. So tick populations are sort of pushed back by freezing conditions during the winter. So the winter freeze knocks back our tick populations, and then they they recover during the summer. So if we're getting less freezing during the winter, then ticks are not going to be set back as much over the winter, and so there's going to be more of them to start off with when spring rolls around. So some species are benefiting from these changes, other species are being harmed by them. Another important element of this is that a loss of sea ice is creating new opportunities for shipping routes and mineral exploration. So it would cut a lot of time off of ships trying to get from, say, Europe to China, or from the east coast of the United States to the west coast of the United States, if they could go through the Arctic Ocean instead of having to go through the Suez or Panama canals, much less down around the bottom of Africa or South America. Problem is that there's usually sea ice in the way. The ocean usually has too much ice on it for ships to go through. But if the sea ice continues to melt, we will have open shipping channels through the Arctic Ocean, which will be advantageous for whoever can send their ships through there. You also have lots of minerals in the Arctic that are just not economical for us to extract right now because the polar conditions are too harsh. They're buried under tons of ice. It's hard to get ships in and out to transport what you've produced. But if this ice continues to melt, then that's going to make it easier to get at those minerals. And you may have heard stuff in the news about Greenland recently. That is one of the reasons why the US government has been making noises about taking over Greenland in some way, is because there's a potential for mineral resources there that the United States would like to get our hands on. So when this ice cover is reduced, we get a feedback effect. So this is what's called a positive or amplifying feedback. So a feedback can be positive or amplifying, or it can be negative or balancing feedback. So a positive feedback or an amplifying feedback is a process in which one change in a system causes another change, which in turn amplifies the original change. So the original change becomes even greater due to its own effects. And so I prefer the term an amplifying feedback because that describes what's happening, that the original change is getting amplified. But you often see the term positive feedback. And so that's positive in a purely numerical sense, that the original effect gets bigger. But it can be a little misleading because calling it positive might make it sound like you're saying it's good. A positive feedback isn't necessarily good or bad. It's just one that increases the original effect. Similarly, a negative feedback is one where the effects of some change lead to a reduction in that change. That balances things out, keeps things in balance. And so that's not negative in a judgmental sense, like that's not negative in the sense that it's bad. it's just negative in a numerical sense, that it reduces the size of that original effect. So what we're seeing in the Arctic is an amplifying feedback known as the ice albedo feedback. So if we have increased temperature, then that leads to melting of the sea ice, right? The less sea ice because it's warmer, it can't keep it all frozen. But when the sea ice melts, that decreases the albedo of the ocean because you're taking what was a very high albedo, right? Bright white ice that was reflecting away large proportions of the sun's energy, like 80% of incoming solar radiation gets reflected away by clean ice and snow. If you're replacing that with ocean water, which is very dark in color, it's going to have a very low albedo, right? Is going to only reflect away, 10 or 20% of that incoming solar radiation. So now you're getting a lot more energy being absorbed because the albedo has decreased. And decreasing the albedo will lead to increased temperatures, right? If you're absorbing more of the energy that hits the surface, that's going to increase the temperature. And as the temperature increases, that's going to melt even more of the sea ice, which is going to decrease the albedo even more, which is going to increase the temperature even more, right? So each step of this feeds into the next one and increases the overall effect. So the ice albedo feedback is a positive or amplifying feedback, where increased temperatures lead to changes in albedo that make temperatures increase even more. So in order to stop this feedback, you would either need to introduce some countervailing force, right? Something else that's going to decrease the temperature and offset this feedback, or it's possible for this feedback loop to just run out of room to go. So once we've melted all of the sea ice, you're no longer going to have this ice albedo feedback because further warming isn't going to change the albedo once it's all open ocean. But until that happens, while there's still sea ice to be further melted, you're going to get a feedback that's going to continue to increase your temperature. All right, so another important consequence of climate change is sea level rise. So we can measure the increase in sea level around the world. And we primarily do that using satellites. So we can use satellite data. Our satellites know exactly where they are in their orbits, and so they can measure, bounce a signal off the Earth to measure exactly how far away the Earth's surface is, and to a very fine degree, they can measure whether the surface of the Earth, including the ocean surface, is rising or falling. And so we can see that sea level is on an upward trend. So the graph there goes from about 1993 to 2018 and shows an increase of about 8 or so centimeters in global sea level. So we can measure that sea level increase, and that sea level increase is due to two main factors. So two main ways climate change is raising our global sea level. So one is that we're adding more water to the ocean, and that's due to the melting of glaciers that are sitting on land. So we've got alpine glaciers in mountain systems all over the world. It's little mountain glaciers. And then we've also got our giant ice sheets in Greenland and Antarctica. So as those land-based glaciers melt, that meltwater runs off into the oceans. We're adding water to the ocean. Ice that's already in the ocean is not contributing to sea level rise. So the melting of sea ice is not going to raise global sea level because that ice is already in the water. It's already contributing to the water, right? So it's like if you have a glass of water with some ice in it and the ice melts, it doesn't cause your glass to overflow because the ice is already in there. So the melting of sea ice is very important. Right? It contributes to that ice albedo feedback, for example, but it's not going to raise sea level directly. Whereas the melting of ice that's on land, because it can then run off into the ocean, will cause sea level rise. So that's one component. The other major component of sea level rise is thermal expansion of ocean water. So as water gets warmer, it actually expands in volume by a tiny bit. So it's too small for you to see with your naked eye. If you're like watching a pot of water on the stove heat up, you're not going to be able to notice that increase. It's a very, very tiny amount of swelling in that water, increasing in its volume, a very, very small amount as it gets warmer. But when you add up that expansion across the volume of water that you have in the ocean, right? We got enormous volume of water in the ocean, and that expansion only has one direction that it can go, right? The expansion can't grow the size of the ocean water, down or to the sides because it's blocked by the seafloor and the edges of the continents. So all the expansion has to go upward. So when you add that up over the size of the entire ocean, you get some significant changes there. And so the graph there actually breaks down the role of thermal expansion and melting glaciers. So you can see adding water from melting glaciers is contributing a little more, but they're both significant parts of the picture. They're both making significant contributions to the overall amount of sea level rise that we are currently seeing. So we can already measure increases in sea level. So this is just our global average on this graph. So in particular locations, a specific beach or a coastal city or something, there may be other factors affecting the local sea level there. If you have erosion or deposition going on, that can affect the local sea level at that spot. You have post-glacial rebound, where areas that used to have giant glaciers on them during the Ice Age, the rock actually got pushed down by the weight of those glaciers, and it's continuing to kind of rebound. It's continuing to bounce back up over the 18,000 or so years since those glaciers melted. Growth of coral in areas that are coral-based islands and so forth. And so there are these different factors that might affect the specific sea level at a specific location. But when we look globally at our changes in global sea level, that's really being driven by these two major processes of melting of land-based glaciers and thermal expansion of the water already in the ocean that add up to several centimeters worth of sea level rise that we can already document having happened over the last couple decades. Another consequence of climate change that we can measure is hurricanes. So a hurricane is a tropical storm that officially, to be called a hurricane, you have to have winds at least 119 kilometers per hour. So if your winds are weaker than that, we call it a tropical storm or a tropical depression. So that's just the official cutoff for counting as a hurricane. So a hurricane forms because water is picking up energy as it evaporates and then releasing it when it condenses. And so we talked about that process when we talked about how things like sweating cool you off, right? Because as the sweat evaporates off your body, it's picking up energy from you and cooling you down. But then when water condenses back into liquid form, it's going to release that energy. And so the release of energy from water vapor in the air condensing out into little droplets of water that form the clouds that we can see when we look at a hurricane, that condensation is releasing energy, and that energy is powering that hurricane. So the energy of the winds in that hurricane are being driven by the energy released by this condensation of water. So because of that, we can infer that if the water in the ocean is warmer, we're going to get more evaporation, which means more energy that's going to be able to be released into the storm. Right? Warmer ocean water, more evaporation, more energy being sucked up through the process of evaporation, but then released in condensation as that water vapor comes back into liquid form to form the clouds that make up the storm. So warmer water ultimately leading to more energy in the hurricane. So we would expect to see changes in hurricanes as a result of climate change warming our oceans. So the strength of a hurricane, we can just talk about the wind speed, but we can also, for simplicity's sake, divide it into categories. And that's what you'll often hear if you're listening to the weather report. They're talking about an approaching hurricane. They talk about which category it is, which category it might be expected to increase or decrease to. over the next few days or something like that. And so this is using the Saffir-Simpson hurricane wind scale, which is just a set of categories based on the speed of the winds and also on the observable effects of those winds. So what kind of stuff are those winds blowing around? What kind of damage are they doing to buildings and trees and so forth, that allow us to determine how strong that hurricane is. And so it's a 5-point scale. So category 1 are the weakest hurricanes, the storms that are just barely strong enough to be a hurricane. And then category 5 is the highest category, so that has the strongest winds. And so correlated with the strength of the winds is what's called the power dissipation index. So that's a measurement of how much energy the storm is releasing. So the wind speed is going to correlate with the energy being released because that energy is driving those winds. So we've got this 5-point scale for how strong hurricanes are. Category 5 being the strongest hurricanes, the most ones with the fastest winds, the most energy being produced, and therefore doing the most destructive damage when they hit land. So let's look at our data about hurricanes. Excuse me. So here we've got data on the total number of hurricanes in the Atlantic. We're focusing in this case on hurricanes in the Atlantic Ocean that are, striking places like the Caribbean and the southeastern United States. Since we're, studying here in the United States, we're looking at our local hurricane issue, right? So for Atlantic hurricanes, this is showing you historical records of the number of hurricanes. And so the red line is the ones that actually reach the shore of the United States, so ones that actually hit land in the United States. Then the green line is the total number of hurricanes in the Atlantic. So you can see, of course, that's higher because there are a bunch of hurricanes that didn't hit the United States. And then you'll also see that there's that orange line that says total hurricanes adjusted. And you'll see that that line is higher than total hurricanes, but ends in about 1970. So this gives us an interesting little insight into the ways that we gather this kind of historical data. So the record of hurricanes in the United States is pretty easy to put together because whenever a hurricane would hit the United States, somebody would notice, somebody would make a record of it, right? Somebody was living there and had their livelihood ripped apart by this hurricane, and could make enough observations that even if we don't have direct measurements of wind speed, we can use the Saffir-Simpson scale to see, was this a hurricane-sized storm, and if so, how big was it? So any hurricane that strikes the United States, we're going to have a record of. Going back, this graph goes back to 1880, but of course we can extend this back even farther if we wanted to. Hurricanes total are going to include all these hurricanes hitting the United States. And they're going to include hurricanes hitting anyone else. So they're going to include hurricanes hitting people in the Caribbean. They're going to include hurricanes hitting ships out at sea. So we can compile all those observations to determine how many hurricanes we had during a given year. But if we are only counting hurricanes that someone was there to observe, that someone got caught in the middle of, there are going to be some that we're not going to notice, because there are some hurricanes that form and then blow themselves out over the ocean without ever hitting land. And so if a hurricane were to form, cross the ocean, blow itself out before it reached land, and also not happen to encounter any ships along the way, then that hurricane wouldn't enter those records. So there are missing hurricanes if we're looking at the total number of hurricanes for the entire Atlantic based on these historical records of people writing down in their diary or writing a story in the newspaper about being hit by a hurricane. There are going to be these missing ones that no person experienced, so they didn't get recorded. So the adjustment there is to adjust for hurricanes that might have occurred in areas where nobody would be there to observe them. And you can see that that difference sort of decreases over time because you have more and more people out there, more ships on the sea, etc., more chances for somebody to encounter a hurricane. But then we stopped doing the adjustment once we get to the 1970s. And you may be thinking, I've been hearing about the 1970s a lot in this lesson, and this is another case that hits in the 1970s because that's when we started having satellites regularly observing the Earth. And so once we have satellites, those satellites can see a hurricane regardless of where it is in the ocean. So those satellites have enabled us to easily count all of the hurricanes, even if they didn't hit anybody, even if no person experienced that hurricane. So before satellites, we have to put this record together using observations of people that got caught in the hurricane. After 1970, we have satellite data that allows us to observe hurricanes wherever they may be, and so we no longer have to do that adjustment. So that tells you something about how we know something about hurricanes. Now, if we look at this graph and we look at what this graph is telling us, what we see is that there's not really a big trend in the number of hurricanes in the Atlantic over this period. So we're looking at this period because this is the period we have temperature reconstructions for. And we saw from some of our earlier graphs that we've got some pretty big increases in global temperatures over the period from 1880 to the present. But we don't see a corresponding increase in hurricanes. Right? We also saw a decrease in snow and ice cover over that period, but we're not seeing a trend in hurricanes. So the number of hurricanes doesn't seem to be affected, at least thus far, by climate change. Warming waters are not creating more hurricanes. But number of hurricanes is not the only thing that we might look at. We also might look at the strength of hurricanes. So this is that power dissipation index that I mentioned before. The power dissipation index, a measurement of how strong the hurricanes are, the amount of energy in our hurricanes each year. So if we look at our historical reconstruction of the power dissipation index, we do see a trend. We see an increasing trend in power dissipation index of hurricanes, and that seems to track pretty well with our sea surface temperatures. So not just our overall global temperatures, but specifically the sea surface temperatures, which is what we would expect to be feeding into hurricanes, right? It's the warming of our sea surface that creates that greater evaporation that leads to a strengthening of hurricanes. So we do see this increasing trend in the strength of hurricanes. So we can say that our measurements are showing that climate change is not leading to more hurricanes, but is leading to stronger hurricanes. So stronger hurricanes, but the same number of them is what we can observe from our data that we have on hurricanes. And these graphs that I grabbed here are a little older. They go up to 2018, but those same trends have continued over the subsequent years up to the present. I just didn't have the updated graphs handy as I was putting this PowerPoint together. Okay, so then that leads us to a final issue to discuss, which is attribution. Attribution is the process of determining the degree to which a particular cause is responsible for a particular effect. Can we attribute that effect to that cause? So in the case of climate change, we're talking about whether we can attribute a weather phenomenon like a heat wave to climate change. Is climate change the cause of this heat wave? Is climate change the cause of this storm? Is climate change the cause of this flood? Right? Whatever sort of weather event we're looking at, is this being caused by climate change? So in the last few years, we've seen some big advances in attribution science, our ability to tease out whether the specific conditions within a particular event, a particular heat wave, a particular storm, were the conditions in that event due to climate change. Right? Did climate change make that event happen when it wouldn't have happened otherwise? Or usually we think in terms of, did it make that event more severe than it would have been otherwise? Did it turn a little flood into a big flood? Did it turn a little hurricane or a tropical depression into a big hurricane, category 5? So we've gotten increasingly sophisticated ability to do this. And what you see in the graph there is a compilation of 170 studies of particular weather events and looking at whether they found that that weather event was attributable to climate change. Did climate change make it more severe or more likely to occur? Did climate change make it less severe, less likely to occur? Or was there no influence? Did climate change not affect that particular event? And then some of them, there were insufficient data, they were inconclusive, they couldn't say for sure. So you'll see that there are a ton of heat waves that have been analyzed and found to be attributable to climate change. Lots of droughts attributable to climate change, lots of rain and flooding events, lots of ocean-based changes attributable to climate change. Then you'll see under the cold, ice, and snow category, a bunch that were attributed negatively to climate change. Climate change made them less severe, less likely, right? Because climate change may be increasing the strength of our hurricanes, but it's also decreasing our ice storms by making temperatures warmer so they aren't freezing. Right, so we increasingly have the ability to do this on a relatively short time scale. So within a week or two after a major event, you often see reports coming out about attribution of that event to climate change. So we've gotten a lot better at this, but there are still big uncertainties associated with it. These attribution studies are not, 100%. They have some error range to them. And they depend on a lot of complicated math that's hard for folks that aren't climate scientists to evaluate. And so in general, and especially in the immediate aftermath of an event, when we don't have attribution studies yet, it's usually safer to say climate change is making events like this more common rather than saying climate change caused this event. So if we were to have a big heat wave, it would be reasonable to say climate change is making heat waves like this more common, rather than to say climate change caused this particular heat wave. So I will leave you with that observation and see you next week.